Hello, Devoxians. How are you today? Awesome. How many of you have been yesterday on the party? Let's raise your hand. OK, I see some hands up. Great. So today, I will talk to you about the memory leak, which we faced in one of our Java applications after migrating to the Google Kubernetes engine. My name is Damian Gałka, and I'm working for Sabre, leading technology provider for the travel industry. We booked more than 1 million trips for our customers every year. We have offices around the entire world. And what is worth to introduce as a context of my presentation is that in 2020, we signed the partnership with Google, and they are helping us to perform the tech transformation and move all of our applications, which we previously have deployed on premises, to the cloud. So just to provide you some background, I asked our AI colleague to provide some description what the memory leak is. And it is a programming issue when the memory is allocated by the process, but not correctly released again to the operating system. So I asked him the second question to give me even 5 reasons of the out-of-memory error killed signal in the container where we deployed the Java application. And I got some answers which are more related to the configuration, which could be due to some real bug in the application which were developed, or which could be caused by the data which we process, or how the data is processed by multiple threads. So what happened actually in our case? We migrated over 60 applications written in different programming language. Most of them were written in Java, but we also have applications written in C, in Python, and so on. We migrated, we switched DNSs, sync databases, we executed performance tests, integration tests, we performed tests with our customers. We felt very confident that everything is working fine. And after first few hours, we saw that, yeah, that's true. Our SRE metrics were looking good, green, no impact to the customers. But we start seeing that, oops, our infrastructure reporting some problems. We checked it out that one of our downstream service is reporting very high memory usage over the time, which causes the container restarts. We quickly verified that fortunately, there's no impact to the customer, as this is downstream service. We have the retries in place. Every request were queued on the message queue, so we do not have any problems with the customers and with their business. We are making bookings, so everything is working fine. So we tried to first increase this memory limit on the container to 4 gigabytes. It didn't help. We increased it again to 8, and we started intensively looking to this problem. We did it to just remove the noise generated by these errors, as we acknowledge that, yes, we have an issue, and we would like to understand what is going on. So in the past, during the preparation to the cutover, we find out the extremely useful tool, NMT, which is acronym from the native memory tracking, which is available in the JVM as a feature and can be enabled, and provides you a great level of granularity for different categories of the memory, which is managed by the Java. So it is not only about the JVM heap, but it's also about all the other categories and areas which are important from the management of the memory in the Java. So we checked it again, but on the production use case. So first of all, in many of the cases, we noticed that problem is with the configuration of the heap. But this case, heap has been limited. It fluctuates nicely over the time. No abnormal activity or the garbage collector. So it's not the problem here. we pulled the details from the NMT, and we made a baseline, and we checked this issue over the time when the process is reaching the memory limit. But as we noticed, the non-heap value, which is reserved by the Java, keeps on the same level. So what is going on? Why Java is not able to actually find out where it is done, where we see that increases and why it is not visible? And it's clearly stated in the documentation of an NMT that this feature is only limited to the memory which is actually allocated by the JVM. And it makes sense, right? So we start Googling and reading how actually the memory is pulled from the operating system and assigned and used by the processes. And we identified that our default memory allocator is from the standard glib library. And it has a concept of arenas. There we have one main arena, which is used to initialize the process and keeps all the static data. But we can have also multiple different arenas, which are created depending on the load and number of threads, which are trying simultaneously to read and write to the segments of the memory. So it's actually a feature to improve the performance. Within each of the area structure, we can identify the heap, which is allocated with the continuous segment of memory equal with the 64 megabytes. And this heap is split into multiple chunks, which can be different sizes, can be occupied, can be free. And all of that things are managed by a set of pointers to the chunks to also improve and maintain how this memory is used and utilized over the time. Having that things in mind that we have in the default implementation arenas of the static size of the heap, and this is actually introduced to improve the performance and throughput of that information, we start to be curious what is actually the limit and how it's calculated. Is it depending on the RAM or something else? It is customizable? We would like to know. And as a result, it depends on the compute power, the number of cores which you are providing to your application, to the system where it's running. And it depends also on the architecture of your CPU. So for the 32-bit architecture, it is 2 times, but for the 64-bit architecture, it is 8-time number of cores. So, OK, we have some limit. We move to the Kubernetes. We change the servers, yes? OK, so let's confirm how many heaps we created in our process. So to do that, we read the output from the smaps files available in the proc directory. And also, if you have it already installed in your container, you can use the pmap utility command, which actually reads the same file, but prints the data in the different format. So right now, I would like to show you 3 things which are important from that perspective and which will allow us to calculate the number of the heaps. So first thing is the address, which is available, of course, in the both cases. On the left, we have the output from the smap. On the right, you can see the output from the pmap. And this is the address of the memory. This address of memory has some permissions assigned to it. And of course, it has a size. And to identify how many heaps your process created over the time, you are looking actually to 2 memory segments. So the memory segment should have the permission set to read, write, and set flag to be private only to that process. Visible data should be visible only to that process, not shared between the processes. And the following next segment should have permission set to just private without read and write access. And one more condition which needs to be met is actually the size of the heap. So the total number of memory allocated by two segments should be equal to 64 megabytes. So on the output from the right side, we see that actually we have, in this particular case, 3 heaps allocated. When we went through entire output of the pmap utility command, we noticed that it is even more than 30 another heaps created. And that generates extra gigabytes, which have to be taken from the operating system. So it was not limit at all for us. So the trigger for that issue was actually the servers, which we changed for our application. We moved application from the very small server equipped with only 2 cores to the Kubernetes with the nodes equipped with 64 cores, and we deployed there our tiny application inside the container. And that container were running only with the control group's limit, but reads entire number of cores from the pool nodes where it was deployed. So as a result, we were able to create about 32 gigabytes of extra memory just to improve the throughput for our threads. So hopefully, this limit is also configurable, so we can change it with providing the value for environment variable called malloc arena max. So we deployed our application 4 times where we had the same code base, the same configuration for application, but only we changed the value for these environment variables. And for yellow, blue, and orange lines, which represents the utilization of that process over the time, we limited the number of arenas respectively to 2, 4, and 8, but the green line represents the deployment with no limit, so with the default setups based on number of cores. As this feature improves the performance, we were aware that it will impact also if we didn't adjust it correctly. So we find out that the 8 arenas is actually the value which satisfies our needs. And we performed the extensive performance test to prove that the same deployment without that limit will crash over the time when the limited one will be able to survive. So I would like to share with you a few checks which you can apply to your migration plan to make sure that it will not happen to you. So first of all, let's document and be aware about your existing JVM settings, not only including the heap, but all the other from the from an NMT. Another one, please also make sure that you are aware about your server configuration, like the CPU numbers, the RAM, but also the environment variables. And lastly, please make the correct adjustments if you are configuring the Kubernetes resource memory limits. It is absolutely not enough to just set it equal to the value of heap. It is absolutely not enough to set it just to value of heap plus non-heap. You also need to remember that we could have some files on the file system which will be cached and loaded to the memory to improve the performance, and still our operating system can generate some overhead which needs to be balanced. So please also leave some buffer for that purposes. And if you are looking how to use NMT, it is a simple JVM option which you can add to your Java process, and you can pull that data with the J command. This command has a very nice feature to set the baseline, which you can execute on the early stages of your execution plan, and later you can just pull the difference between the executions. If you are looking how to pull the memory from the containers, you can look to the files which are managed under the C group directory, or you can use the smaps or execute the pmap utility command. Is it anything to tune the memory allocators? Yes, of course. You can do it as we did by the malloc arena max environment variable, or you can even consider changing the memory allocator to tcmalloc, jmalloc, or memalloc. If you are looking for more information, I recommend you that articles which you can easily find on internet. They help us a lot in making our analysis. And also you can reach me out. You can send me an email. You can find me on the LinkedIn. And also I encourage you to visit our sales booth on the first floor near to the chill-out zone. And I really enjoyed to have you here and to speak to you. So thank you very much.